we're going to continue talking after the Desmos activity yesterday. We're going to talk about limits. And limits are really the basis of calculus. Pretty much every theorem that we would have, if you were going to prove the theorem, you would base it off of limits. So let's look at the notation first. So the notation, and you should take notes on this because you're gonna need these, especially for the Delta Math assignments. So take the notes, please. If you look at and you are asked for a limit as f of x, a limit of f of x as x goes towards some value c, if it equals a finite value L, if we were to read that out loud, this is the limit of f of x as x goes to c. So some different things on this, okay? This right here is some sort of a function. Okay, could be a graph. Could be just an equation. Something like that. It could be either one of those. If it equals a finite value, this is a y value. I'm going to put it in quotation marks mainly because, it could be another variable, not y, but it could be v or something like that. It could be a, could be p for position, something like that. This right here is an x value. I'm going to put that in quotation marks also because it could be a t value if time is the independent variable. That's kind of the gist of what the limit notation is. So it's where is a graph going? So it's different than what the actual function equals. So this is really, a limit refers to is really the behavior of a graph, or what y value is a graph, and I say graph because it could be an equation, a graph going to. I don't know if there's two O's in that or not, but I'm going to put two O's. Where's a graph going to? So where is it? I don't think there's two O's actually, now that I think about it. So if there is, sorry, English people. So it's behavior of a graph, or it's, where is a graph going to? So where is it going? That's what a limit is. That's what a limit refers to. It would be the kind of thing if I drew a graph, maybe I drew a quick graph, something like this, drew some axes, and I put a little graph in here, and let's say I even had an open circle here, and I had this, and let's say this is value c, and this is some function f of x, and this is some value L, some y value. This is x. And if we were looking at something like, what is the limit as x goes towards c of this function f of x, in this case, it would equal L. Even though there's a hole there, what we're doing is we're kind of saying, getting closer and closer to see if we were traveling on this graph like it were a road, where is it getting to? What, as we move along the x-axis from either direction, as we get closer and closer to this value c, what is this graph getting to? And in this case, it's getting to the value L. It may never get there, and that's not really an important thing. It just we need to know that it's approaching there. So it's the behavior of the graph. Kind of leads us into the next thing. In order for a limit to exist, it must, the function, actually, I'll just write that. No, I'm going to write the limit must, look at that, sorry, must approach the same value from the left and the right. So, in order for a limit to exist, it must approach the same value from the left and to the right. Go back up to this one. Notice that that limit does exist because the limit is approaching the same value. And when we're talking about the same value, we're talking about the same y value. So let me put that in there, the same y value from the left as it is from the right. If you're approaching a different y value, or you're going to infinity or negative infinity, we say that that does not exist because you can't get there. So it has to be the same finite value. So what I mean by that is we can look at things called one-sided limits. Okay, so one-sided limits. From the left side. From the left side, we would have the notation, the limit as x goes towards some value c with a little negative after it of f of x. Okay, that's the left side notation. From the right side, so that little negative kind of refers to from the left side. So let me put a little highlight on that here in pink. So this is signifying left side. From the right side, you can guess that then that notation would be the limit as x. I'm actually going to move that up because if I turn this into a PDF, it won't show up right. So hold on. The limit as x goes towards c from the right side of the function. So that little plus mark signifies the right side. So let me explain what that looks like. So if I were going to draw a graph, and let's say I draw a graph and I have this function. So this is f of x up here. This is x down here. Let's say I have a graph that goes like this. And let's say I put an open circle right at this value c. And then move up here and we go up here. And let's just call this L1. And let's call this L2. If we were to look at the one-sided limits on this one, so if we were to take this graph and I were to say the limit as x goes towards c from the left side of the function, it is equal to L1 because we're talking about coming from the left side of c. moving this way. That's L1. But I could also look at the limit as x goes towards c from the right side, but that's equal to L2. Notice that if I'm coming from the right side, from the orange tick marks to the right of C, if I'm traveling along this road, I'm getting to L2. In order for the limit, so a little side note here, something that's really important. In order for the limit as x goes towards c of f of x to exist, it must approach the same value it's the same y value from the left as it does from the right. It has to approach the same value. So in this case up here on this graph, I'm going to scroll out to there. Oh, I don't think I can scroll all the way out. This particular example, the limit, in this particular example, if I were going to write it, the limit, let's scroll in a little bit because my writing gets bad if I don't, as x approaches c of f of x does not exist or is undefined. It's approaching a different value from the right as it is from the left. In that case, we say the limit is undefined. Now, all of this is a little different than if you were just talking about what f of c was. F of c is the value, it's really the y value of the function at x equals c. That's just a y value. In the example that I have up here, if I were going to figure it out on this one, f of c equals L2. Okay, so if I just asked you what f of c was, it's L2 because that's where the dot is. The limits are talking about something different. The limits are how we're traveling on the graph. Okay? There's some different properties that I'm going to go over right now, and then we'll be done. And then you'll have a chance to do a Delta Math assignment. So I need you to write down these properties of limits. The first one, the limit as x goes towards c of, let's say if the limit as x goes towards c of f of x is equal to L, and the limit as x goes towards c of a different function, g of x equals k. So let's say those two things. Then here are the following properties that you have to know or understand. Number one, the limit as x goes towards c of f plus or minus g is equal to L plus or minus k, meaning you can evaluate those limits independently and just add the values together. Two, the limit as x goes towards c of f of x times g of x. So if you multiply those, you can just multiply two values of the limit, and you're good. 3, the limit as x goes towards c of some constant times the function f of x. So this is a constant is equal to that constant times whatever that limit is. So that's like a vertical shift up is what it really is. So it's just a constant times the limit. Something that happens with powers, the limit, or actually let's do division, as x goes towards c of f of x divided by g of x is equal to L divided by K, with the only stipulation is K cannot be 0 because you can never divide by 0. That doesn't work. 2 more. The limit as x goes towards c of the function f of x raised to a power n is equal to n, or L raised to that power. Remember, we're going all the way back up, and we're basing it on these two properties up here at the beginning, this property and how we're generically defining it. So down here, that's what I'm referring to as L. The last one is the following. The limit as x goes towards c of f of g of x. Generally speaking, that would be f of k, provided f of k exists. Okay, so it's got to exist. So if it doesn't exist, we could have issues. Okay, that's all the notes. If I went too fast, you always have the opportunity to pause it, go back, review it, watch the video again, take the notes, then go back and watch the video again. Go on and now do Delta Math assignment, and I will see you very soon.